Thank you for taking the time to look into our presentation. My name is Remco. I'm an NPI project leader at Wilting. NPI stands for New Product Introduction. And today I'm here together with my colleague Raymond.
Hello, my name is Raymond Haasma, working as team lead additive manufacturing at Wilting. The topic of today is manufacturing of high precision metal printed parts with low stiffness in a 24/7 production environment.
For today's presentation, we will show something of Wilting, and we will go into detail of the topic that Raymond just mentioned. So the schedule for today is a company introduction, a definition of what are high precision metal printed parts with low stiffness, what are the challenges for these specific products, what do we have as a solution, a short conclusion, and some guidelines to help you with designing such a product.
The introduction of the company Wilting. Wilting specializes in the production of high-value precision components, complex sub-modules, and assembled parts. Our expertise in milling, 3D metal printing, and cleanroom assembly position us as a trusted partner for European OEM companies operating in high-tech industries such as semiconductors, aviation and aerospace, medical systems, and automotive sectors. We offer our customers effective industrialization for efficient production.
So, what does it mean? Effective industrialization for efficient production. As Raymond mentioned, Wilting has a lot of experience in different industries on high value precision components and complex modules. And with these products, we see several stages from talking with the customer on what the requirements are and what the possibilities are, all the way to 24/7 production in bigger batches. There are several stages, but basically we can split them up into effective industrialization and the production process afterwards in higher volumes. So for the industrialization, we have a new product introduction team, the NPI team, and that's the team that will talk with the customer on what the requirements are, on what the possibilities are. And that's the team that will have a look into the organization. How can we set up a product like the customer wants to have? We have a structured process and special resources available for developing such a first product. And the main focus during this stage is feasibility and on timing for the first prototype or first product that the customer would like to have. Continuing, we are going to focus more on the efficient production, and that is when a small series, a second series, or a third series will come, and we will prepare ourselves for a bigger quantity and also a man-independent production process. We strongly focus on lean to see only the essential steps to produce the product. We want to have it operator independent, and we want to have it 24/7 produced. That is the focus in the efficient production phase. And when that one has been done successfully in the NPI stage, we will transfer it to our supply chain. And for these products, we have in-house cutting-edge technologies for precision milling, 3D printing, clean room assembly, and also ensuring quality with our quality department.
Precision metal printed parts with low stiffness. These parts are characterized by specific features and requirements. As first, the parts are manufactured using additive manufacturing. This process involves layer by layer deposition of metal powders, which allow for complex geometries and complex design to be realized. Next are elongated thin-walled features, typically around 0.5 millimeters in wall thickness. This design feature results in low stiffness, providing flexibility and elasticity to the components. Low stiffness is often desirable in certain applications where some degree of flexibility is required. Also, these parts have very tight tolerances, typically within a few microns. The precision is required to reduce stresses introduced to the flexible part, possibly leading to failures over lifetime. The picture on the right shows an example. References are in the center of the geometry, and a profile accuracy of 20 to 40 microns is placed on the tube ends, where the tube length can go up to 250 millimeters. These parts are also in high volume demand that requires continuous and uninterrupted production processes, with the possibility to produce at night and in the weekends without the need for operators. In summary, high-precision metal printed parts with low stiffness are 3D printed components made from metals like titanium or stainless steel. They possess long, thin-walled features, have tight tolerances, and require high-volume production. These parts are used in applications where precise dimensions, design freedom, and flexibility are essential. So what is the challenge for us as the manufacturer? In this slide, you will see the general process flow of 3D printed parts that are being post-machined. First, we have to start with engineering, so defining the printing model and making the toolpath for milling. Second, 3D printing. Then comes the heat treatment to anneal out the stresses in the part. And EDM, so using a wire to cut them off from the build plate. Then we have to finish the printed parts, so removing the support structure, improving surface roughness, or etching, for example, can be used. And then comes the machining, and then cleaning and qualification. So a quite large process flow. It first starts with 3D printing, and those parts are generally rigid on the build plate with supports. And deformation can occur or will occur because of stresses in the material during 3D printing. Then we have to machine that part where the support is already removed. So it's come from being a rigid part to a part with low stiffness and relatively flexible. And the flexibility brings the risk of clamping induced deformation. So imagine clamping the part with a clamp that deforms the parts for like 0.1 or 0.2 millimeters, and that's not allowed if we have to realize the precision of 20 to 40 microns. And that deformed parts brings the challenge of a 24/7 production, because when there's variation in the process, it's not possible to have an unmanned process. So there's a constant need for skilled operators. So close collaboration is required between those steps. So we start with the risk assessment together with the team and see which risks are in the process and mitigate them, because the base material is very expensive. When something goes wrong with machining, we have to throw away a lot of value, but also a lot of time. So for example, when there's not enough material on the part to post-machine it, has a big impact. Or when there are burrs getting inside the part, that also gets a lot of impact, because we have to go back to 3D printing again. So having a good risk assessment is essential for these parts.
So continuing with the solution that we have for these complex, high accurate and low stiffness products. And in general, we have a good alignment between the experts that we have on printing, milling, assembly, and on measuring. And that is guarded by the new product introduction project leader. That project leader will take care of the organization and continuation of the project, and will make sure that all these experts are aligned throughout the whole process to ensure a high quality and producible product. Specifically for these products with this low stiffness, we have additional things that we do, and one of them is temporary stabilization. Unfortunately, we cannot share too much about this production process, but what we can share is that we have a temporary stabilization to fixate the product and make sure it is rigid enough for the milling process. And in this case, it will introduce a minimal amount of stress, so the product will not deform too much afterwards. What we additionally do is we use advanced CNC machine probing. So before milling, we align the product with the program for milling, because each individual printed part is just a little bit different compared to the others. Additionally, we have the statistical process control. This means that during the milling, we take measurements of the product, and these measurements, they can be compared to the previous products that we have created. So we can see if everything's in line, if some measurements and some steps in the process are more difficult, and we can take action if necessary to make sure the output is good. And that's the way we control the variability of these printed parts. The conclusion from previous slides is that with these additional things, measurements that we take, we can offer a stable 24/7 production on these high precision, low stiffness parts. And this way of producing in these parts, they have some good advantages, and that is that basically you can have the freedom of 3D printing, lightweight design, internal features, complex geometries, and you can combine them with high precision, even up to a few microns with the milling process. We can make it repetitive, so we can continue, have a good output, stable output, and it's scalable as well. So those are some of the great advantages. But of course, this production process also has some disadvantages, and that is, in a very early stage, it's fundamental to think about which production process will be used, subtractive or manufacturing or additive, so printing or taking it from a block of rough material. And it's quite important to do it in an early stage, because otherwise a lot of time and money will be wasted for the whole process. The whole process takes longer than it does for regular products milled from just a block of material. So it's quite time consuming, especially for these complex geometries. And also the validation for printed parts is quite a bit more of a challenge than for regular parts. So for example, you have CT scans that need to be done to see if the printing was done well. And also measurement on these low stiffness parts is quite a challenge, because your measurement devices will also bend the product a bit. So this will take additional time to have in the MPI process. And also there's the limit of the current materials that are available or specifically available, perhaps for some of the suppliers. So that's also something to take into account. And to help a bit on designing, we would like to share some do's, some tips, and also some of the limits of this production process. And some of the do's are definitely use the freedom that you have with 3D printing, and focus on the functional requirements that the product needs. Also keep in mind some of the potential deformations that might occur, but also definitely use that freedom that you have. So for example, at the bottom, you can see a picture of a sliced through product, and this product is printed, and normally it's within a closed environment, so this would not be possible to manufacture with just a milling process. This is something you can only do with the printing. So have an additive manufacturing way of working and mindset when designing such a product. Another one is what is very important is to use a good reference system for your dimensions, because each individual printed product might be a bit different, and also some deformation, even the slightest deformation, might occur. And when using these points as a reference, it might mess a bit with your dimensions and might make it quite more complex or more costly to produce such a product. So having a good reference system is very important. Also, what could really help is have early involvement from experts or from a good supplier to review the design and give feedback on what could be improved. It's still a developing technology in general, so there is a lot of things ongoing. There are software packages that can help predict. There are software packages that can help you to design such a product. So make use of them, or make use of the supplier that can help you with that. Some of the limits that we see are, of course, the general limits that we have with printing. That is with the angle of printing, that is with the building volume that you can have within your printer, that is with the available materials, so keep that in mind as well. Till now we see a particle cleanliness up to ISO class 1, which is quite good, and it's still developing, so who knows how far we can get into the future. Another limit that we see, also referring to the product that is mentioned in the picture of this small heat exchanger that is printed, is the wall thickness. It should be at least bigger than 0.4 millimeters to have a gas-tight application, and it is because printed parts have a similar density to the normal material, like a brick of material that you would use, but some pores might occur. And you need to have this minimum amount of material to ensure a gas-tight application in case of some pores occur. Also, the distance of internal channels should be at least 0.5 millimeters to have a successful depowdering, because with the printing within the product, the not printed parts will be powder, and afterwards you want to remove it, so you need at least 0.5 millimeters to have it successfully out of the product. And hopefully that will help you to design, and of course feel free to contact one of your experts or suppliers, and hopefully that will be Wilting. We will be very willing to help you with some of the questions that you might have, or even with some of the products you like to get our experience and get our experts involved in creating it and designing it, and hopefully even producing it.